All right, the second question on the concept list is asking to determine values where a function is discontinuous. The most common examples of these are where you have a function that has an expression with x in the denominator, or a piecewise function. So we're going to walk through these two types and show you kind of what to look out for. So when you've got an expression that has a function in the denominator, so x minus 4 is a line, what you're going to do to find out where that function holistically is discontinuous is just set the denominator equal to 0 and solve, because that will give you the number that causes dividing by 0 to happen. So in this case, you just have to add your 4 over, and that's where your positive 4 is coming from. In the case of this particular function, it's the location of a vertical asymptote when you look at the graph. The second piece is a piecewise function. It's got 3 different parts, and it's split up by the x values on the graph. So this function is defined as a constant at 11 when x is -1. I'm going to kind of give you a visual of what this looks like. So from -1 going to the left, we're at this constant 11. So I'll give you an 11, give you a -1. So from here, not included over, you've got this piece of the line. And then this x squared plus 2 is a parabola, and it's happening from -1 to 3. So here's about where 3 would be, and in this middle part you've got a parabola. So usually our x squared is at the point 0, 0. This one's been shifted up here, and we're connecting in some sort of way here. Now what I want to talk about is whether these actually connect with the parabola or not. And that's really testing whether these are continuous or not. We're looking at this point -1 where it's been being split in from one function to the next, and we're just seeing if they match. So I know that this one says not included, but right up next to it, we're almost at that 11 value. Okay, we're almost there to -1, and it's at that height of 11. So what we're going to test is, on the other side, is it still almost at that 11 value? So you'll just do direct substitution here, -1 squared plus 2, and see what happens. So -1 squared is 1, plus 2 gives you 3. So at -1, you're actually only at a value of 3. So here's what your parabola looks like. We've got this happening here, and then it keeps going up to some value here. Well, that's what we're going to check next, is what this value is. So at 3, same thing, we're going to plug it into that equation. 3 squared plus 2, that gives you 9, plus 2 is 11. So here is where this one stops, and my sketch is a little bit off, but it's just to give you a visual of what's actually happening here. So now we're going to the last piece. It says it's also at 11 if it's greater than 3. So this piece, from an open circle this way, is back at 11. So here's what we're looking for. We're basically saying, does the first piece pick off where the second leaves off, and does the third pick up where the second left off, and so on. So here, because there's this gap here, these weren't at the same value, then the graph is discontinuous at that value of -1. Over here, you could continue this curve without picking up your pencil, so it's not discontinuous there. So our only value that causes problems is the -1. So you can do this graphically, kind of like what I did through here, or really you can evaluate the limits of the function as you come from the left and as you come from the right, just by switching from one equation to the other. Okay, you're doing direct substitution at the values they give you, and just subbing in and seeing if they're equal.